Is Philippe there or is he remote as well?
Yeah, he's here. He'll be right after you, I think.
Okay, very good. Yeah, a little while ago I saw a video being played with ice, so I figured it was him.
Oh, yeah. Checking the Zoom link, I think.
Yeah.
All right, so everyone, welcome back to the last session of the meeting. Um, so it's a pleasure to have Dave Nicholls next, and he's going to tell us about Dirichlet-Neumann operators for Laplace's equation with quasi-periodic boundary conditions, analyticity, and computation.
Very good. Thank you very much, John. And thank you to the conference organizers for inviting me. I should apologize. When I accepted the invitation to come and chat with all of you, I fully intended to come out to Toronto and spend a delightful week in Canada in June. And then through a sequence of events, none of which are interesting, it turned out I had to teach in the summer school. So this is the final week of the 4-week session of summer school, where I've delivered 44 regular lectures in 11 sessions. And today was the last day, and tomorrow's the final. So I had to do it from here, and it was extremely painful. And for that reason, I really have not been able to participate in this meeting at all, which is a real shame because I really like the look of a lot of the talks that were on the list. Um, in addition, I've spent a lot of time in Zoom in the last 4 weeks. So I was in Zoom for 3 hours this morning, teaching a very uninterested group of people the method of separation of variables. So I'll give it my best. I will try to be energetic and entertaining, but you'll forgive me if I fall just a little bit short. So this is work with John and Jin Yu, and it's handy that John's in the audience and is ringleader. If you have any very difficult questions, you can just ask him, and I'm sure he'll get you all sorted out. So some references to this work with John and Jin Yu. We have this paper in Studies in Applied Math from a couple years ago, and that's what I want to talk about today. And there's ongoing work, and I was hoping that Jinyu could be here to present that, but that's all right. We'll discuss it all at some point in the near future, I'm sure. This work is inspired by a line of papers that I read by John and Jinyu on related problems, also addressing quasi-periodicity. And I read these papers and I thought, it's a great idea, and this is the sort of thing that we could bring to the problem of computing Dirichlet-Neumann operators. So we did it. First, a sequence of obligatory photos that every water waves talk needs to have. We need some pictures that come from Wikipedia pages, and the first one is of a solitary wave. Oh, let me just make sure I've got my chat up in case anyone wants to say anything. The point of which is to show, water waves are interesting, but they show different patterns. So here's one pattern. It's a two-dimensional or probably one-dimensional shape, and it's characterized by, well, the bump in the middle, but then sort of decay to some sort of quiescent state as you go far away to the left, far away to the right. But there are other shapes that one can see on different Wikipedia pages. And here's a famous one from the 1930s where you see swells coming in to the coast from the ocean. And you see this sort of conoidal behavior. It's solitary-ish looking waves, but in a periodic pattern. So not decay towards a quiescent state as you go to plus or minus infinity. And then if you search around towards the bottom of this page, you find even more striking photos. And so this is not just a single train of waves coming in towards the coast, but now you have the interaction of different trains of waves coming in, and you get really quite beautiful patterns. So it depends on how you look at it. Maybe these are rectangular, maybe these are hexagonal, Who quite knows? It's a little bit difficult to tell, but it's clear that there's all sorts of interesting surface wave patterns that you can notice in the ocean. But on some level, these are all very specialized. So we had sort of the decay at infinity. We've got periodicity in 1 or 2 dimensions, depending on how you want to count these things. And this is sort of doubly periodic. But most waves don't really look like either of these. And so this is a picture I saw in a talk of Bernard de Koninck, um, from a park that he was at in Washington State. And you see, my goodness, it can really get quite complicated. And that is definitely not a shape that's showing decay to infinity. It's not showing any sort of simple periodicity. So if we want to simulate waves that look like this, if we want to simulate other physical problems that show such complicated shapes, we need another notion, and quasiperiodicity seems to be one approach to this that people have taken, and that, as I said before, I think we can accommodate into our study of Dirichlet-Neumann operators. So these are the sort of patterns that we're after. So why Dirichlet-Neumann operators? Well, first of all, they go by many, many names. Dirichlet-Neumann maps, DTN maps, Steklov-Poincaré operators. My advisor, Walter Craig, liked to call them Dirichlet-Neumann operators, so that stuck with me, DNOs. And they arise in all sorts of problems of applied interest. So I also spend quite a bit of time thinking about the scattering of linear waves by periodic structures, acoustic electromagnetic waves, and definitely Dirichlet-Neumann operators come up in these circumstances. And the challenge here is that the shapes of the structures can be very irregular. So how do you build that into your modeling? They come up in free boundary problems like obstacle problems, and they come up in moving boundary problems like the water wave problem, which I'm sort of thinking about in the front of my mind in this talk, although these other problems are in the back of my mind as I give this talk. So they can be used for a number of purposes. The most obvious one from our perspective in modeling water waves is for dimension reduction. So if you have an ocean which features fluid, which is largely, I don't know, homogeneous, and it's beneath air, then it would seem kind of wasteful that you were going to do, say, a numerical simulation where you discretize into the water and into the air. It seems like everything you would want to know could be recovered from what happens at this free interface between the two um, uh, materials, the air and the water. And so a Dirichlet-Neumann operator allows you to restate a problem that would otherwise be volumetric in terms of surface quantities. Now, in the background, of course, there's some sort of volumetric solve, which is built into the definition of the Dirichlet-Neumann operator, but never mind that for the time being. Another way Dirichlet-Neumann operators come up, which is less obvious in this context, but comes up a lot in, say, electromagnetics and acoustics, is for domain truncation. So in an electromagnetic problem, you have light illuminating some sort of grating, and things scatter off to infinity. And so doing a numerical simulation where you attempt to discretize at infinity is going to be doomed. And so you have to do something to make the domain finite. And so Dirichlet-Neumann operators are a faithful way of doing this, which you have to decide, are you willing to put in the extra work, computational, theoretical, in order to get things just right, or are you going to somehow approximate the action of the Dirichlet-Neumann operator? All right. So never mind all those generalities. Let's think about a specific problem that hopefully will be interesting to some people here in the audience, that of modeling deep gravity water waves. So we've probably had a number of water waves talks so far, and Philippe is about to give another one. The equations for an ocean wave with a free interface are well known. And the model is roughly the following set of Euler equations, perfect fluid equations. Laplacian of a velocity potential phi is equal to 0 on the domain where the fluid exists. And then you need some boundary conditions at the free interface to tell you how the interface is going to move. So you have a kinematic condition, which tells you that particles at the surface don't go flying off the surface. So the time rate of change of eta, the interface separating the fluid from the air, plus, and now you've got a normal derivative, dy phi minus, plus x derivative on eta, x derivative on phi equals 0 at the interface. And then you've got a Bernoulli condition, which says that you satisfy the equations of fluid mechanics. So in all of this, g is the gravitational constant, and phi is this velocity potential, so that if you have the velocity potential everywhere, you can reconstruct the velocity by simply computing its gradient. Now, as I have instructed my students this summer, time and time again, you cannot just specify a differential equation and expect to get a unique solution. You just specify side conditions as well. So on some level, we've got conditions at the top. We also need conditions telling us how do things get started. So we supplement this with initial conditions for phi and for eta. And then we need conditions in the far field and laterally. So physically relevant solutions have vanishing vertical velocity as y goes to minus infinity. And if you've got a fluid of finite depth, then you just say that the y derivative of phi equals 0 at this finite depth. And then we circle back to this question of what do waves look like laterally? So if you're interested in modeling the solitary waves from the very first picture that I put up, then you might consider the lateral boundary conditions from this first bullet point. Decay as x goes to plus or minus infinity. So eta should go towards 0. And phi, well, I don't know it needs to go to 0, but it should go to a constant as you go to plus or minus infinity. Phi is only defined up to a constant anyway, so maybe that's going to be okay. But now if you're interested in modeling what was going on in the second and the third picture, with planes going over the ocean and sitting up on top of your lighthouse, then what you want to investigate is periodicity. So you've got some lattice capital gamma, and as you move around through this lattice, you repeat yourself. The phi repeats and the eta repeats. And so it seems like much of the research that's done in water waves considers one or the other of these two boundary conditions. So it's rare that you see something much different. And I think one of the things that truly struck me about this work I read John and Jin use is how they were bringing into the field of water waves, a new class of boundary conditions that really are very important, and a methodology for actually investigating what these solutions could look like through a notion of quasi-periodicity. So before coming to that precisely, let me just show you with some specific examples how Dirichlet-Neumann operators are useful, parts 1 and 2, dimension reduction, and domain truncation. So first off, Zakharov told us back in 1968 that the water wave problem could be viewed as a Hamiltonian system if you just picked the right variables. So the right variables are the interface eta, and then the velocity potential at eta. So I'm going to give a name to the velocity potential at eta. I'm going to call it xi. And then Walter Craig, my advisor, and Catherine Sulem pointed out in their 1993 paper that while this restatement was perfectly fine, you could make all of the dependence on these two variables more explicit if you use the Dirichlet-Neumann operator. And so you can think to yourself, all right, I want to solve Laplace's equation, which is at the heart of the water wave problem, on the domain y less than eta, supplemented with Dirichlet data at the top, the right boundary condition as y goes to minus infinity. I know that if I give good lateral boundary conditions, like decay at infinity, or periodicity, or perhaps even quasi-periodicity, then this Laplace problem will have a unique solution. And from that, I can produce Neumann data, for instance, external pointing normal derivative at the interface. And the mapping, G, which accomplishes this task, mapping Xi, the Dirichlet data, to nu, the Neumann data, is our DNO. It depends on the interface, eta. And so if you believe in this Dirichlet-Neumann operator, you can restate the water wave problem in the following set of red equations here at the bottom of the slide. Time rate of change of eta is the DNO applied to Xi. And then the time rate of change of Xi is, well, now you have to sort of chase around the chain rule, minus G eta, and then kind of a nonlinear combination of the Dirichlet-Neumann operator and x derivatives of Xi, the tangential derivative of eta, and then x derivatives of the interface eta. And if you want to do three-dimensional waves, that's fine too. You just get a couple of extra terms in this second evolution equation. And so indeed, you can reduce the problem from the entire domain, in theory, to one just at the surface in terms of the surface quantities, eta and Xi, where you have to understand that solving in the bulk of the fluid is built into computing the Dirichlet-Neumann operator. Now, all of this is fine, but the Dirichlet-Neumann operator problem still is posed on a domain of infinite extent, which is okay until you want to code things up on a computer, in which case you decide, well, I need to make that infinite domain, semi-infinite domain, into something finite. So what we've always done is introduced an artificial boundary at, say, y is equal to minus a, which is strictly below the lowest point that eta ever gets to in the L infinity norm. And what you do is you have two sort of coupled problems. You have a Laplace problem from minus infinity up to minus a, and then you have a problem, Laplace problem, from minus a up to eta. And the problem from minus infinity up to minus a, you can solve explicitly, provided you specify data at minus a. So if you specify this data, call it psi, you can introduce a second Dirichlet-Neumann operator, which maps psi, that data at minus a, to the normal derivative at minus a. And then you can link that back to this problem for v, the quantity you started with what looks like a tautological boundary condition here at minus a. The y derivative of v at minus a should match the y derivative of w at minus a, which is specified by the Dirichlet-Neumann operator. And so if you enforce this condition, you transparently enforce that the solution exists with a boundary condition at minus a rather than going all the way down to minus infinity. And so this is what we'll do in our statement of this problem. But the idea is that we want to accommodate periodicity, which is quasi-periodic, and we want to be able to compute this very first Dirichlet-Neumann operator, capital G. All right. So there's a number of notions of quasi-periodicity or aperiodicity or any number of other quantities that one could consider. And there's this lovely review paper, SIAM review paper, 1966 by Jürgen Moser, where he talks about all this, not for water waves, but in the context of celestial mechanics and other problems. And so one definition that John and Jinyu found particularly compelling, and you can see why, is the following one. So he says that a function f is quasi-periodic if there is a function f tilde, which is defined with a higher dimensional independent variable. So f goes from Rn to R, f tilde goes from Rd to R, and d is going to be greater than or equal to n. And f tilde is going to be periodic with respect to the lattice 2 pi z to the d power. So it's a nice 2 pi periodic function in all of these d dimensions. And the relationship between f and f tilde is through f of x is f tilde of kx, where alpha is kx, is a new higher dimensional variable than x. And the key is this matrix K, which is d by n, if you're chasing down all the dimensions that it needs to be. And the periodicity or quasi-periodicity of F is characterized by this matrix K. Now, in a couple of slides, we're going to want to change variables from the x's to the alphas. So it's good to know how things change. The gradient in x changes to the gradient in alpha, but with a K transpose put out front. And then the Laplacian with respect to x changes into kind of the Laplacian in alpha, but you've got a K tilde in the middle. Now, if d is equal to n, so if k is square and it's invertible, then the f that you generate is just periodic with respect to the lattice gamma characterized by k. If d, the dimension of the alpha, the new variable, is strictly bigger than n, then it could be that f is still periodic. For instance, if n is 1, so x is just one-dimensional, and if d is 2, so our new variable is two-dimensional, then the matrix K needs to be 2 by 1. And if K is, say, 1 and then a rational number, then in fact you are still periodic. If the rational number is Q over R, a little calculation shows that your function is still 2R periodic. So to get something genuinely not periodic, something genuinely quasi-periodic, what you need to do is you need to populate your matrix with some irrational entries. So the simplest thing is when n equals 1 and d equals 2, and k is 1 kappa, and kappa is irrational. So in this way, you can do something that's genuinely different than what's been done in the past. So here's a plot from John's paper with Jin Yu. And here they're computing traveling wave solutions, which are quasi-periodic. And so I believe that eta is in blue and xi is in red. And these are quasi-periodic functions where the kappa was chosen to be 1 over root 2. And a nice way to think about how this is all generated is to plot the function f tilde, well, it's eta tilde in this case, which is represented by the level sets that you see here. So d is equal to 2, but you are not claiming that this is the surface that you're computing. The surface you're computing is, well, follow these dashed lines, starting at the origin and going along with slope, I believe, 1 over root 2. And then it's periodic. So you have to find over here on the left where you intersected, and you continue on and up, again, with a slope of 1 over root 2, and you hit, again, one of the edges, and so it's periodic, and so you're following around this two-dimensional torus along this line. And so that is what's tracing out this complicated shape that you see up here on this slide. So it's a beautiful way of encoding rather complicated-looking behavior in lower dimensions with a higher dimensional object. So what they did was for traveling waves, and then I think evolving water waves eventually. But I thought that what we could do is we could bring all this to the problem of computing the Dirichlet-Neumann operator. And it would be great to do some nice numerical simulations and hopefully prove a theorem, which we're able to do with a bit of difficulty. So really the definitions I've given so far for the Dirichlet-Neumann operator don't really depend all that strongly on the particular boundary conditions you put on them. At the end, you just say things are quasi-periodic. But now, if you have a numerical bent to your mind, like I do, you start to think to yourself, all right, well, how are we going to simulate all of this numerically? So you get a little sad because trying to find a good way to numerically approximate a quasi-periodic function seems pretty fraught from the start. It is almost certainly going to have discontinuities anytime you try and make something finite. But if you think of things in terms of, rather than the quasi-periodic function itself, but rather its envelope, so rather than eta, xi, and nu, the eta tilde, the xi tilde, and the nu tilde, Now you become much happier because those guys are nice and periodic. And so you're thinking to yourself that a really straightforward Fourier spectral method should do a fantastic job of approximating the tilted quantities. And then once you've computed those well, going back to the untilted quantities is, well, you just need to evaluate at kx. And so that was the plan. So what you want to do is you want to recast all of the governing equations in terms of the tilted quantities. And you can do that without too much trouble using these rules that I gave for how gradients and Laplacians change. And it all looks fine. And perhaps you get a little bit nervous because you start seeing things like k tilde. But I don't know, maybe it's going to be fine. In fact, the appearance of operators like this make things much more interesting. But we can actually work our way around them. So the thing to keep in mind is that we are introducing quasiperiodicity to this problem, but we're only doing quasiperiodicity in the lateral directions. We are not also doing quasiperiodicity in the vertical direction. If you do that, then operators like k tilde appear also in the y derivative, and it becomes an extremely difficult problem. Okay, so we've written down these equations in terms of the tilted quantity v and xi, and we want to produce the tilted nu. And now the Dirichlet-Neumann operator, tilted, maps the xi tilde to the nu tilde. All right, so there's all manner of numerical tools available to you once you've recast things in this way. And there's lots of great volumetric methods, finite differences, finite elements, spectral methods. And this is great. You could code all of these things up if you'd like. But they're a little wasteful for the problems that we have in mind because, as I mentioned before, probably the fluid is going to be rather homogeneous and the air is going to be pretty homogeneous as well. You should be able to get away with just simulating at the interface. And so boundary integral, boundary element methods are available. And in fact, methods inspired or incorporating conformal maps have been extremely successful. There's a number of papers and codes available for this. John and Jinyu use this in computing their quasiperiodic traveling waves. And it's great. These all perform very well. However, there is a big jump when you go from a two-dimensional to a three-dimensional setting. So for the boundary integral element methods, you have to switch to a new fundamental solution, which introduces new difficulties. And well, conformal maps work great in the two-dimensional problem, but in the three-dimensional setting, they're not available anymore. So I in my group, have experience with a class of methods, which we've called the high-order perturbation of surfaces methods, HOPS methods, because we all need an acronym. And they're a compelling class of schemes where they are applicable. So there's a perturbation somewhere, and the perturbation is in the size of the deformation of the wave shape from the quiescent state, flat. And so these are not so great if you want to do overturning things, but you don't always want to do overturning things. If the shape of your wave is not too far away from flat, then these methods not only are applicable, they can be highly accurate and they can be very, very fast. And then you can circle back and see that in fact, you can do quite large perturbations if you can do numerical analytic continuation. And I believe John talked this morning about Pade approximation, and that's absolutely the approach that we've taken to these problems in the past. Now, before we get too deep into the numerical simulation, it'd be nice to know if we specify eta tilde and xi tilde in some reasonable function spaces, does the DNO even exist? So that would be unfortunate. If we're going around trying to find this operator that doesn't even exist in a good way. And if so, what are its mapping properties? With the idea that this Dirichlet-Neumann operator one day can be glued into a traveling wave solver or a solver for the evolution problem. And so in this paper with John and Jinyu, we wanted to not only do some numerics and show that we could compute things with a high degree of accuracy, but we also wanted to build up towards a rigorous numerical analysis by at least showing that these DNOs exist in a good way and show that they exist analytically as a function of this perturbation parameter that's associated to these high-order perturbation of surfaces methods, basically the height or the slope of the interface. So there's a number of hops methods. The one that produces the best numerics and allows you to prove theorems is the so-called method of transformed field expansions, TFE, which was something that I investigated with Fernando Reitek many years ago when I was a postdoc. And it's sort of based on the low-order calculations of Rayleigh and Rice, back from the turn of the previous century and the middle of the last century. And their calculations, which they took to very low perturbation order, 1 or 2, were taken to much higher order by, well, first of all, Michael Milder in the context of water waves, and Oscar Bruno and Fernando Reitek in the context of electromagnetic scattering problems. Although the methods that they used couldn't be used for a direct proof. So our contribution was that we took this other approach where we do a little transformation first, and now all of a sudden you're able to do proofs and the numerics turn out to be much more stable. So the idea behind the method of proof is it's simply the method of majorance from PDEs. And I learned it from Avner Friedman's papers and books. So I sort of view it as his method, but he definitely didn't invent it. But it's really rather straightforward. So you've got a perturbative frame of mind, but before you start perturbing anything, the thing to do is to change variables. So you've got this problem on an irregular domain, and I think this has been talked about a lot in this meeting, and that's kind of a problem. So how are you going to make any progress with things so irregular? And one of the best ways is to make a little change of variables. So we make a very simple one, which has been used by many people. And then you make an expansion of the transformed field and the Dirichlet-Neumann operator in a regular perturbation series. And then you estimate these quantities using well-known tools from the theory of partial differential equations. Elliptic estimates, which are deep and subtle, but which we did not invent, and recursive estimates and certain algebra properties. And so you bring together a bunch of things that are already known in this unique way, and you can get analyticity of this field and the Dirichlet-Neumann operator without too much difficulty. So how does it go? So the change of variables is called different things in different fields. It's called sigma coordinates in oceanography. It's called the C method or the Chandazon method in electromagnetics. And it's a simple domain flattening change of variables. You leave the lateral variable alpha alone, and you map from y to y prime through y prime is a, y minus eta, over a plus eta. So that eta maps to 0, and minus a maps to minus a. And so you now search for the transformed quantity u, which is v after this mapping, and it satisfies a set of equations which looks very similar to the set of equations that was satisfied by v. So the left-hand sides are all the same. It's this sort of Laplacian on the left with, well, the kk transpose thrown in. And then you've got this Dirichlet data equality at the top. You've got this transparent boundary condition at the bottom. You've got periodicity, but there's a cost to making this simple change of variables, which doesn't have any special geometric properties. And the cost is that you introduce right-hand sides to the Laplace equation and to this transparent boundary condition. And the point is that these guys are indeed non-zero, but they depend on eta. And they depend on eta in that they are big O of eta. So as eta tilde gets very, very small, these guys vanish. So these are the first corrections in a perturbation expansion in powers of eta, if you will. You can write out what they are. Here's an example, or a term, one of the terms in F tilde, the right-hand side. It's the gradient of u, but inside a divergence. But yes, here's a power of eta, and you've got this kk transpose in the middle there. So it suggests that if you set eta tilde to be epsilon, I don't know, F tilde, then you could think that a perturbation expansion in this small parameter epsilon for the field U tilde and the Dirichlet-Neumann operator G tilde might be successful. And so you can plug this in, and it's regular perturbation theory. And you find problems that govern the nth correction to this. And the left-hand sides all look the same as the previous. And then you've just got these right-hand sides, where Fn depends on alpha and y. But it also depends on F tilde and the UMs, but for M, which is strictly less than N. So things that you have already found at previous perturbation orders. And now here's the scheme. We're going to show inductively that you can bound these UNs and these GNs. So start with some base case where N is equal to 0, which, truth be told, is just the flat interface case, which we can solve exactly. And then given that you've got estimates on the UN and the GNs for all little n less than capital N, show that you get an estimate in the order capital N case. And the trick is choosing the right function spaces for the U's and the G's. So for this, we have some designer Sobolev spaces. So we're going to use, it's supposed to be absolute value of P, but you don't want to divide by that when P is 0. So add in a 1. So bracket P squared is 1 plus absolute value P squared. TD is the d-dimensional torus. And then we have these classical interfacial Sobolev spaces for the functions like C tilde and nu tilde, where you express these as Fourier series, and you simply demand that the Fourier coefficients decay fast enough so that when you sum bracket P to the 2s next to the Fourier coefficients of Xi squared, you get something finite. So that's the HS space. For the volumetric functions, like the field, we're going to demand sort of lateral regularity, but nothing special in terms of vertical regularity. So vertically, it's just sort of L2, but laterally, we're demanding HS. So it's just like the norms above, except you're taking the L2 norm in the y direction as well. All right. So it's instructive to see what we've accomplished to compare what we did in the periodic case a long, long time ago with Fernando and what's coming in this quasi-periodic case. So in the elliptic case, genuinely everything was classical, and we just did some explicit calculations because things were periodic to show that in that special case, we were recovering what was known more broadly in the elliptic case. So in all of this, we noted that the right-hand side F could be written in divergence form. And so we estimate solutions of an elliptic problem in terms of these forms, Fx, Fy, and F naught, where there's an x derivative on the Fx and there's a y derivative on the Fy. And in all of this, we took advantage of this Fourier multiplier, which is this bracket on P on the Fourier side, which has this notation on the real space as bracket D. And it's like taking a first derivative, except you can divide by it without worrying about the zero wave number. And so here's the elliptic estimate that we effectively proved. So if the Dirichlet data was an HS plus 1, and if the J, so the J is what comes up in the right-hand side of the transparent boundary condition. So it's like a y derivative of the field. at the boundary, if that's an HS, and if the right-hand sides are in this XS, but half a derivative is an XS, so the FJs are kind of in XS plus a half, then you can say the following thing about the unique solution of the DNO problem. So the left-hand side really kind of feels like HS plus 3/2. And in fact, you can say that where the HS plus 3/2 is both in the X and the Y variables. But here we're really making a big deal about the X regularity. And well, we do have a Y derivative here, but really in the Y direction, it's just an L2 estimate in this norm. And it's bounded by the things that you would expect on the right-hand side. So the HS plus 1 norm of C, the HS norm of J, and then the right-hand sides. And it feels like U, in solving this DNO problem, gains a derivative on these right-hand sides, which are themselves inside divergences, and loses a little regularity as you go to the boundary by a half. So all of that balances out. And so if you prove this elliptic estimate, you can now use it to solve the Dirichlet-Neumann operator problem for the capital Nth correction of U. So it's like the XS plus 3/2. It's like these first two terms, d 1/2 dy un, and then d 1/2 gradient un, both measured in the XS plus half norm, can be bounded by the right-hand sides. And here's one of the terms in the right-hand side. There's an f grad x un minus 1. And that guy has already been estimated. When you use an algebra property to pull out the CS plus a half plus delta norm of f, you get what you desire, provided you choose B big enough. So it's got to bound this 2m over a and this norm of f, CS plus a half plus a little bit, plus delta. So with that little algebra property and with this elliptic estimate, you can use an inductive method to show this analyticity. So what's different in the quasiperiodic case? Well, in the quasiperiodic case, what you can do is you can follow what we did in the periodic case. You express your unknown function, u tilde now, in a Fourier series, but now it's a Fourier series on the higher dimensional torus. You take this and you plug it into our governing equation for the DNO problem, and you find this two-point boundary value problem, two y derivatives on u hat minus this k transpose p squared, u p hat equals the right-hand side. And so this k transpose p is what comes from, squared, the divergence alpha k transpose grad alpha. So if there was no k there, this would just be absolute value of p squared, and that would be the periodic case. Okay, so wherever you saw absolute value of p in the periodic case, you now just put k transpose p. And to see the problems, you can say, never mind the f. Let's just solve this problem with f identically 0 with just the c and never mind the j. So that can be integrated, perhaps even by the students I've been teaching this summer. And you find that the solution is the Fourier coefficient of c times this function, this exponential, e to the absolute value k transpose py, which is good as y goes to minus infinity. It actually decays. So now you want to estimate in these designer function spaces u. So you're going to be integrating this u hat p, L2, and you can work out this integral and you get this thing, 1 minus exponential of minus 2 absolute value k transpose pa, all divided by 2 k transpose p. And now the thinking is, Okay, so for p small, you just have to make sure that you're not dividing by zero ever. What really matters in terms of these estimates is what happens as p gets very large. So you're thinking that as p gets very large, this exponential term is going to go away. And this L2 norm of EP is going to behave like, I don't know, 1 over p. And in fact, that's exactly what happens in the periodic case. So that as expected, you gain half a derivative as you come from the boundary into the interior. However, in the quasi-periodic case, that is not what happens. Because what happens is, for most of the p's, k transpose p gets very large as p goes to infinity. However, for a set of p's, which is infinitely big, you get directions where k transpose p in absolute value stays very, very small, even as p gets very, very large. And so rather than gaining this derivative as you come into the interior, the best you can say is that you maintain the same regularity. What's worse, it's the same phenomenon. You can think to yourself, it seems like this operator, k transpose p, is going to play a big role in our analysis. So we can think about it as an operator acting on surface valued functions. Well, in the periodic case, that is an operator that takes a derivative. And as long as you stay away from the zero mode, it's got an inverse, and the inverse gives back that derivative. In the quasi-periodic case, that is not the case. So indeed, k transpose d takes a derivative, as you would expect. However, this guy does not have a good inverse unless k has got entries which are, well, in the case we're talking about, 1 and an irrational number. So if the second entry is a rational number, for an infinite number of p's, k transpose p is 0. So you get an infinite number of zeros. But even in this case where kappa is not rational, still the k transpose p gets very, very small. And it's an instance of small divisors. And so the best that you can hope for is to do something like what Moser talked about, is to say, okay, the k transpose b's get small, but they get smaller, no worse, than gamma p to the minus r. And so even if you put in a condition like that, you can define the inverse operator, but not only does it not give you back a derivative, it actually takes r many derivatives, which is very aggravating. So we were a little worried that our analysis was going to be doomed, and it seemed that way, but Jin, Yu, and John worked very hard, and they showed that, in fact, it's going to be okay. Because it's not that you ever have to worry about 1 over k transpose p in isolation. There are always other terms that come along in our analysis, which, well, they don't give you what you want, but at least they prevent bad things from happening. So for instance, in this L2 estimate of EP, a lot of the time you get the 1 over p behavior that you want. But along that line, in the lattice, where things are going badly for the denominator, at least in the numerator, there's something that cancels it out. And so you don't get 1 over p decay, but at least you're like a constant. And so because of all this, you can get an elliptic estimate to work out that looks like what we had in the periodic case. It's just that it has to be that you're estimating terms like u and these gradients of u and the y derivative of u with derivatives in front estimated by the right-hand sides. Now u tilde is only in excess, even if the f's are in excess. But it turns out that's good enough so that you can turn the crank on this theorem much in the same way we did with Fernando all those years ago. Now, there are some additional wrinkles, and that is that you need to have this algebra property where you no longer have a regular derivative, but you have this Fourier multiplier, k transpose d to the 1/2. And so it gets a bit more involved, but you can get it to work, provided you use the HS plus a half norm on F tilde. But it did require some new technology. So in the end, we were able to show the theorem that the field itself depended analytically upon epsilon, even in this case of quasi-periodic boundary conditions, provided that S was bigger than D over 2. So we use this embedding result. And furthermore, you can get estimates on the size of the derivatives of these UN tildes. With this, you could then estimate the G tilde and show that this Dirichlet-Neumann operator on the higher dimensional torus was also analytic. So there are some estimates. And then we coded everything up. And I will not share with you the details of these other methods, operator expansions and field expansions. But we did code up this transform field expansions approach. And we got some results compared to a class of exact solutions that made us very happy. So there's a lot on this slide, but I'll point you towards the yellow and the black. So these are results from our transform field expansions approach, where we've used Taylor summation and Pade summation. So what does this refer to? Well, you don't do an infinite number of terms in your perturbation expansion. You truncate after a finite number, say 16. And then the question is, how do you sum the thing up? Well, you just sum it up as a truncated Taylor series. That's the Taylor approach. But it's been known for a long time that you can enhance your results by approximating this truncated Taylor series with a rational function. And Pade gives a particular formula for recovering the coefficients in the two polynomials, and we used equidimensional Pade approximates. So in this case of a small perturbation, our approaches get us down to 10 to the minus 12 accuracy, and somehow that's limited by the solver that we implemented in the y direction. But now if you make the epsilon bigger, you start to see our new approach come into its own. And here the black and the yellow are producing extremely good results, 10 to the minus 5, compared to these other methods, which are becoming a bit of a disaster because of cancellations. And I'll close with this result here, where we've chosen a perturbation epsilon so large that the Taylor series approach with our stabilized numerics is actually diverging, which means that we've chosen a value of epsilon which is outside the disk of analyticity. However, there's still a domain of analyticity outside the disk. And if you use numerical analytic continuation, you can hope to access this. And so we did using Pade approximation. And here, the errors are about 10 to the minus 4 by the time you've done 16 perturbation terms. So I'll just close with that. And thank you very much for your attention.
Thank you. Any questions for Dave?
If you take a Liouville number or a Diophantian number, it is change something or not at the numerical level?
I'm sorry, what was the question again?
For quasi-periodic function, you say that you take an irrational number in order to have a real quasi-periodic, which is not periodic. Is it change something if the number you choose is Diophantian or Liouville? I mean, very close to rational or very far to rational number?
Oh, that's an excellent question. So we simply chose, I think it was just root 2. But of course, on a computer, that has to be represented as a rational number. But it would be interesting to rerun the numerics if you chose something that was, I mean, you can imagine there would be sort of stabilization by discretization. So small errors are going to render your computations perhaps a little bit more stable than they actually are. But what if we made the kappa a rational number and it was like 1 over 2? Yeah, we did not do that calculation. I want to do that now. That's a very good question.
I think you just get a family of periodic solutions. Like you're solving a bunch of DNOs together at the same time, periodic ones.
Yeah, but I wonder if we start dividing a whole bunch of things by 0 in the code, and then the whole thing just kind of blows up. But I'd be curious to see what happens.
Question. We are a little bit over time, so I want to make sure that Philippe has enough time. So thanks a lot, Dave. That was great.
You're very welcome. Thank you.
Yeah.
So I'm going to stop sharing